Hi, welcome to this particular module, and in this module we will see another kind of oscillator that are called unijunction transistor oscillators, or they are also called UJT oscillators. Alright. So, when we talk about UJT oscillators, we have to understand what are unijunction transistors and why we have to use UJT oscillators. Earlier we have seen different kind of oscillators, right. If you remember, we have seen different kind of oscillators starting from phase shift, Wien bridge, LC, that is LC is also called tank circuit, and using tank circuit we have constructed Hartley, we have constructed the Colpitts oscillator, then we have seen the crystal oscillator. So, let us see how exactly UJT will work as an oscillator. To understand that, we have to see the slide, and we can see that like diodes, unijunction transistors are constructed from separate p type and n type semiconductor materials. Okay. So, you have to understand how UJT works, okay, and hence its name unijunction. Okay. So, you see unijunction transistors are constructed from separate p and n type semiconductor materials from a single p-n junction within the main conducting n channel of the device. Within the n channel of the device you have this p, and that is why it forms a p-n junction, okay. This is a fabrication. Now, you guys know, if I want to dope, let us say if I have a n type semiconductor and I want to have a p type material in n type semiconductor, right. What is the process step? We should all know, right, we should all know. Let us see what are the process step. Okay. So, what I asked is we need a p type material in n type substrate. This is what we need, right. What we will do? We will take a silicon, right, this everybody should know now. We grow oxide, right, this is our oxide. Then what we do? Next step is we have to open a window, right. That means that we will spin coat photoresist. We all know this, right, spin coat photoresist. So, let me put photoresist like this. Now, what is next step? Next step is we will pre-bake it, right. This is photoresist, this is SiO2, this is silicon, this is silicon dioxide. We can grow silicon dioxide using LPCVD. Now, we have coated spin coated photoresist. After spin coating, we know it is time for soft bake, and we already know that whenever we use silicon we have to clean it. Okay. So, 90 degree centigrade, 1 minute on hot plate, correct. Then we use mask, we load the mask. Okay. So, I will load the mask. How my mask will look like? My mask will look like this. It is a bright field mask. My photoresist is positive photoresist, right. We have seen that many times. So, now you should be able to understand. Okay. Still, if you are confused, you ask me, okay, in the forum, do not worry about it. Positive photoresist. Okay. So, now we are loading the mask on the photoresist, that is soft baked. After that, what we will do? After that, we will expose the wafer with UV, correct. Then when we expose the wafer with UV, because it is a positive photoresist, what will happen? This area will be intact. So, we cannot use positive photoresist, is not it, because if this area is intact we cannot create a window. So, here we cannot use positive photoresist, we have to use negative photoresist. Why? Because in negative photoresist whatever area is not exposed will be weaker. In positive photoresist area not exposed stronger, okay, negative photoresist. Area not exposed will be weaker. Okay. What we want? We want that our what we want is that we need to create a window in SiO2 like this, right, so that we can dope p type material, so that we can dope in this area p type material, right. So, to obtain that we have to protect the photoresist on this two area, right. So, our photoresist should be protected in this two area, and from other area photoresist we have to etch out, that we can do when we use negative photoresist with a bright field mask, correct, with a bright field mask. So, after UV exposure we will develop the photoresist, and what we will find after developing the photoresist, we will find that after UV exposure, this one with bright field mask and negative photoresist, what we will find? We will find that the photoresist which is not exposed, so I have to develop it, right. Photoresist which was not exposed got weaker and got developed. Photoresist that was not exposed, right. So, photoresist which is below this area will not be exposed and it got weaker, and then it got developed in the photoresist developer, correct. So, now I have photoresist which is negative SiO2 silicon SiO2. After that I will etch the, so after photoresist is developed I will do the hard bake, I will do the hard baking 120 degree centigrade per minute. It also depends on the data sheet, okay, what kind of photoresist to use. In the data sheet is already mentioned what is the soft bake temperature, how much time you have to heat or bake, same way what is the hard bake temperature, how much time you have to bake, everything is given in the data sheet when we use a particular photoresist. So, you have to look at the data sheet. Okay. So, when we do PR developing and hard bake, you get this particular wafer which is shown right over here. Now, what what we have to do, we have to dip this wafer in SiO2 etchant, SiO2 etchant. What is SiO2 etchant? We all know SiO2 etchant, very easy to remember, buffer hydrofluoric acid, right. That means when I dip this wafer, in the buffer in BHF, what will happen? My SiO2 which is not protected by my photoresist will get etched. Will get etched, right, easy. Now, what I will do? I have to remove the photoresist. So, I will after this, after etching SiO2, I will dip this wafer in acetone, right, acetone, because acetone is PR stripper. So, we have to strip the photoresist, all right. So, what I have? I have a window, right, you see here is a window. Now, through this window what we can do? We can dope the p type material, right, this is n type silicon. So, we can now dope a p type material in this silicon. The SiO2 will not or will act as a mask and will not allow the dopant to enter in this particular region, right. SiO2 will act as a mask and will not allow the dopant to enter in this particular substrate. So, now we can dope using either diffusion or ion implantation, correct. either diffusion or ion implantation. What we can do? P type material, P type material. Once that is done, what is the next step? Next step is I have to again do and again keep this wafer in the BHF, in the buffer hydrofluoric acid, and I will see that the SiO2 is removed. When SiO2 is removed, we get the wafer which is what we wanted, correct. This is how we can obtain a P type doping in N type material, right. That is what it is saying, right. Like diodes, unijunction transistors are constructed from separate P type and N type semiconductor materials, forming a single name unijunction PN junction within main conducting N type channel of the device. Okay. The device with only one junction that acts as exclusively as electrically controlled switch. So, UJT is a non-linear amplifier. It is a low cost and used in free running oscillators, synchronized or trigger oscillators and pulse generation circuits at low to moderate frequencies. Okay. This application. Now, you see here it is nothing but it looks like a PN diode, right, and then there is a resistor due to the B2 here, and then the resistor due to B1 which is here, right. Now, the across the voltage across this one. So, you have base 1, you have base 2 and you have a emitter, right. Emitter is nothing but your P within the N type. Okay. So, you have to understand how the UJT works, then only you will be able to understand how you can design an UJT based oscillators. As you see that it is used as a free running oscillators, it is used as a synchronized or trigger oscillators, also used in pulse generation. So, very important you have to understand. So, let us see working. Okay. Let us see its working. So, resistance R1 and R2 are bias resistors, R1 and R2 are biasing resistors, which are selected such that they are lower than the interbase resistance RB1 and RB2, right. The resistance which is caused here RB1 and RB2, these resistors are lower than the interbase resistance. The resistance R3 which is here and capacitance C1 which is here decide the oscillating rate. This R and C will decide the oscillating rate. Okay. Now, when a voltage Vs is initially applied, okay, when we applied a voltage Vs, you see here across this terminal, the unijunction transistor is off and the capacitor C1 is fully discharged, right. When you apply this voltage, unijunction transistor cannot operate, it cannot operate, right. And what will happen when it is off? C1 is fully discharged, C1 gets fully discharged, but begins to charge up exponentially through the resistors R3, right. It start exponentially through the R3. There is an emitter of the UJT is connected to the capacitor, right. The emitter of the UJT is connected to the capacitor. When the charging voltage Vc crosses the capacitor, becomes greater than diode voltage drop. So, this is PN junction diode, right, we have seen, right. So, when the voltage across this capacitor Vc1, this one becomes greater than the diode voltage drop, the PN junction behaves as normal diode and becomes forward biased, triggering UJT into conduction, right. In this case, when your capacitor will start charging through the resistors R3, this capacitor voltage when it increases more than the PN junction diode volt drop, then the UJT will start conducting. The UJT transistor is in on condition. At this point, emitter to B1 impedance collapses and emitter goes into low impedance saturation stage with follow of emitter current through R1 taking place, correct. So, it is conducting, that is why this is it goes to the impedance collapses, B1 will go to impedance collapses and the emitter goes into low impedance stage, right, it will conduct. So, as the ohmic value of R1 is very low, the capacitor discharges rapidly through UJT, the fast rising voltage appear across R1. So, when it is conducting, the capacitor will quickly discharge through R1, right, it has a closest path to discharge, this is the path to discharge for the capacitor, right. If it is not conducting, capacitor cannot discharge through this path. Now, it is discharging through this path and the resistor across R1, right. Here if I measure voltage across R1, what will I find? Find that the it will result in a fast rising spike. You see fast rising spike, this one. Also because capacitor discharges more quickly through UJT than it does charging through resistor R3, right. This discharging time is lot less than the charging time of capacitor discharges through the low resistance of UJT. Okay. Now cutoff. So UJT cutoff. What is cutoff? This is the region where the unijunction transistor does not or does not yet receive enough voltage to turn on. Okay. So you see here the emitter voltage versus emitter current graph, right, and you can see what is a trigger region, what is the highest peak of voltage, what is the cutoff region, and what is a valley, what is negative resistance region, where is the valley point, where is the saturation region. This everything you need to understand. All right. So go back and see in detail how the UJT works. Okay. Now the voltage has not yet reached the triggering voltage, so transistor will turn on. This is a region where the unijunction transistor does not yet receive this cutoff region, you can see here. Negative resistance region. So what is cutoff region? This is the region where the UJT does not yet receive enough voltage to turn on, and this voltage has not reached the triggering voltage, so that the transistor will not turn on. Okay. Now negative resistance region is, why it is negative resistance region? Why this is called negative resistance region? You see, negative resistance region, right, because when you apply a voltage, right, the resistance should increase or decrease. Suppose particular resistance value, right, keep on applying voltage, what will be the curve of I? Understand that. If the why this is negative resistance, because after the transistor has reached the triggering voltage, the V trigger, it is now turned on, right, the transistor is turned on. After a while, if the applied voltage still increases to the emitter load or lead, it will peak out the voltage V peak, it will reach here, right. So initially it is turned off, then when it reaches this region, cutoff region, right, the voltage the voltage has not reached triggering voltage, so transistor will be on. Now the transistor has reached triggering voltage, which is here, this triggering voltage will turn on. After a while, if the applied voltage still increases, if I keep on increasing the voltage, it will reach its V peak, which is here. Now if it will lead out V peak, from V peak to the valley point, from here peak voltage to the valley point, which is right over here, right. The applied voltage drops while the current though increases. V equals to IR, right. If my voltage is dropping, my current should also keep on dropping, but what I see is that at this particular point, in this particular region, from here till here, right, this particular region, right, what I see is that from V peak to valley point, the applied voltage drops while the current though increases. That means as if the resistance is decreasing, it is a negative resistance, the current increases but the voltage decreases, which is why it is called a negative resistance. Got it? So why it is called negative resistance? Easy, right? Okay. If your answer is it is not easy, then you have to understand correctly how UJT works, then it will become easy. Okay. So whenever I say easy, I assume that you guys have done some homework and you know how the UJT operates. These are basic devices you should know. So saturation region, let us see. After the negative resistance region, which saw an increase in current, comes the saturation region. This is the region where if the applied voltage to the emitter still increases, the current and the voltage will rise. Okay. Now again it will start rising, which is what we are expecting, correct. So if I want to understand the equations, the charging equation of the capacitor is given by Vp into eta Vbb plus Vd, right. Vct is nothing but Vv plus Vbb into 1 minus e to the power t RTCT. This is exponentially, if you see the graph how this equation comes, it is very easy to understand. Alright. Now at Vct, V is nothing but Vp at time t equals to t. So if I substitute the value, right, what will I have? Vp which is VCT equals to this value, using equation 1 which is my value of Vp. I substitute the value of Vp here in this equation number 3, right. From 1 I substitute value of Vp in equation 3, I will get this equation. Now if I neglect the values of Vd and Vv to get approximate relation of T, I can get Fo is nothing but 1 by T 1 by RT Ct log n 1 by 1 minus eta, or Fo is nothing but my oscillating frequency, right. Extremely simple, very basic mathematics, you should understand, you should clearly understand, right. So now I have my oscillating frequency for UJT oscillator. Okay. So this is how the UJT oscillator will work. This is how the UJT oscillator will work. So now what we have seen? We have seen that in case of oscillators, we can have several types of oscillators, and the application of oscillators we have seen mostly using operational amplifier, but in some cases we have also seen a crystal oscillator, we have also seen a UJT oscillator, right. So in general now we have an idea of how oscillators would work, right. So in the next module let us see what is noise. What is noise? What are kind of noise? I will just touch the base, and we will move to the next lecture. Okay. So I will see in the next module. By that time just look at it, how the UJT oscillator works, right. I have shown you in an example how you can fabricate a device very quickly, just recalling something that you are learning earlier. Now you guys can at least understand the process flow for MOSFET as well, right. Similarly we can say n number of circuits we can fabricate if we know the process flow, alright. If you have any question, I will answer your questions, okay. Don't get confused, don't worry, I will answer your questions if you have any. Alright. So now in the next class let us see how the noise, what is noise and what are kind of noises. Okay. Till then you take care, I will see you in the next class.